This call is now being recorded.
Okay. All right. So, hi everyone. I'm Sabina. I'm a TA for 281. I've been teaching this class for like 4 semesters. So, yay. So I'm gonna use an iPad. So please bear with me if I make a mistake or um, if something doesn't work or anything like that. Okay. So, project 1 was due yesterday. So, if you guys want to use a late day, if you submit today, then you guys will be using a late day. And if you submit tomorrow, you guys will be using 2 late days, and you guys only have 2 late days, I believe, even for this semester. Lab 2 quiz is due on 15th, and autograder is due on 22nd, and lab 3 is due. Quiz and autograder both are due on the 22nd. Midterm is on 28th, and we are still deciding on how to give the times, I guess. Last semester we gave 3 or 4 time slots, but we are not sure if we're gonna give that for this semester as well. We're still working on it. We are gonna post a Piazza post about more announcements, more detailed, any logistics that you guys are have questions about, like cheat sheet and etc. And yeah, if you need SSC accommodations, email east21admin at umsh.edu. Also, if you guys have any questions while I'm presenting, just feel free to unmute yourself and ask any questions you have. Okay. Any questions on logistics? No? Okay. All right. So today we're going to go over recurrence relations, vector implementation, especially on resize and reserve, and how amortization plays in how we can analyze the runtime using amortization. And we're also going to briefly go over strings and C strings as well. Okay, and if you have some time, I'll open up the office hours queue, so if you guys need any help, then you can ask me anything. Okay? All right. Okay, recurrence relations. So, if you guys went to the lecture, recurrence relation is an equation that is defined in terms of itself. For example, a Fibonacci sequence you can see as on the slide, f of n equals to f of n minus 1 plus f of n minus 2. So, it's referring to itself. And many algorithms have complexities that are naturally modeled by recurrence relations, meaning there's a lot of algorithms that are just recurrence relations. And I'm going over this quickly because you guys went over this in the lecture. So master theorem is a theorem that you can use to identify the algorithmic complexity of a recurrence relation. So if, as you can see on the slide, T of n equals to A, T of n over B plus F of n. So if a recurrence formula fits in that formula, we can use the master theorem. And master theorem is quite convenient because you can just plug in numbers, and actually like these 3 are the only cases that fits in the master theorem. So if you can identify A, B, and C, then you can use the master theorem. Okay? All right. So why don't we actually try this? So I'll give you guys like 2 minutes, and could any of you guys want to identify what A, B, and C are in this case? You can unmute yourself, or you can put it in the chat. Okay, A is 8, B is 2, C is 1. Yes, okay, that is correct. So you can see, use my pencil. Okay, so A is 8, right? Okay, that's working. All right. B is 2, and C, as you can see here. Yeah, there we go. This is 3, and is, you can drop the constant, so therefore C is 1, right? So we would use this case. because A is A, B to the C will be just 2, right? Okay. Cool. Everyone got that? Any questions? Make sure to have master theorem well prepared, as in like you can identify the constants pretty quickly and which cases to use. Should be a fairly simple question if it comes up on the midterm. Okay. All right. So what if it does not fit in the A T n over B and plus f of n? Then what we can use is we can use substitution method. Substitution method, how it works is given the recurrence relation, we're going to identify the recurrence when it actually uses itself, like this term. And then we're going to substitute itself into the recurrence formula and build down until we reach the base case. Okay. And base case should be given to you. All right. So the steps are first we substitute the formula for T of n into the recurrence relation as you did just now. Well, we're gonna go over more step by step after this slide, and then you should identify a pattern at kth step, and then you're gonna solve k such that the base case is present. Okay. So let's do an example here. If it will, the slide will be. I don't think it's updating on the Google Meets. Okay, there we go. So this is our recurrence relation. So what we're going to do, we're going to substitute the formula for T of n into the recurrence terms. And this is the recurrence term. And so what we mean by substitute the formula for T of n, what we're going to do is we're going to substitute with T of n minus 1 because we want to substitute into here. So then it'll be 2 times T of n minus 1 minus 1 plus 1, right? So here. Does that make sense? Okay, I'm assuming you guys know. Okay. So we're actually going to substitute this into here, right? So we get this, and we'll get that. We expand the terms. Also, don't simplify because what we're trying to do is we're trying to identify the pattern at the kth step. So we're going to see in a couple of slides, but do not simplify yet. All right. So the next thing we're going to do, we're simply going to plug in n minus 2 into the T of n, which should be, oh, not this. Yeah, this one, right? And then we're going to substitute that into here, and we should get here, okay? Do you kind of see the pattern now? Okay, cool. So let's do one more example. At the fourth step, we're going to put T of n minus 4 here, and that should be, right? And we're going to substitute that into here. Wait, that should be, oh, sorry, T of n minus 3. Okay? So at fourth step, how many times did we multiply 2? We multiplied 4 times, right? So if you look at this, this is 2 to the power of 4, and then with a 2 minus 4, right? And this is 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. Do you see the pattern now? So we're going to actually put it into a formula. So on the k step, what it's going to be, T of n is going to be 2 to the power of k, T n minus k, plus minus 1, k minus 2. Does that make sense? Yes? Okay, cool. Because it's really important to know how to substitute and how to figure out the pattern yourselves. It's really important. Okay, cool. All right, I like the response that I'm getting. Okay, cool. So we just did that. Yeah. So you guys all good? Okay. All right. So we have the pattern identified, right? So what the last step is, we're gonna solve for k such that the base case is present. So now that we have identified the recurrence relation, the pattern, we could just use the base case and figure out the algorithmic complexity for this recurrence relation. So we know that the base case is when t of 1 is 1, right? So so we want this base case to be present so we can solve the recurrence relation. So, and that's when t of n minus k is t of 1, which means when k is n minus 1, right? So we're going to substitute n minus 1 for k. So basically we're going to plug in n minus 1 into all the k's here. Okay. So then we should be getting, let's write it out. Okay. And I assume you guys recall this formula from like what? High school, Calc 1 or Calc 2. And you can just plug in these values to solve this. And that should be O to the power of n. Does that make sense? Any questions? Yes? No? Oh, could this be on the exam? Yes, it could be on the exam. So for the midterm, we're gonna give you a practice problems, and you might see substitution methods coming up on the exam, and it wouldn't. Well, I cannot guarantee that it's gonna be this complicated or not, but you guys should be able to do this on the exam, meaning it wouldn't require too much, I guess, memorization of mathematical formula. That makes sense. Okay. Any other question? Am I going too fast? Yes? No? Okay. Cool. Because we have a lot to cover, so just gonna. Okay. If you guys are good, I'm just gonna go to the next slide. Okay. So now we know that given a recurrence relation, we can identify the algorithmic complexity, right? So if we have a recursive function, if we can identify a recurrence relation out of it, then we can figure out the complexity of our function, right? So why don't you actually take 3 to 4 minutes, try to figure. So this is this example, right? It's a code. It's a recursive function. So try to identify the recurrence relation here, and I'll just give you guys 3 minutes to work on it, and then I'll go over it with you. Try to look what the complexity for this line is, and this line is, and this and this. Okay. And this is also a valid exam question, so I really hope you guys do it by hand. And try it right now. Okay, I'll give you guys 3 minutes. Oh, and bar n is log of n. Okay, I'll give you guys 30 more seconds and then I'll go over it with you guys. Okay, so foo n over 4. So we're calling foo, it's a recursive line, right? So this will be t of n over 4. Yes? Because t of n, we're trying to figure out the runtime for foo, which we represent using t of n. So calling foo itself will be t of n over 4. Okay. And then so k is n squared. Just this runtime is just O of 1. Just one simple calculation line. Okay, so what about bar n? Bar n is log of n, right? So this inner for loop, we're running bar n times. So this line will be n log n, right? And then the outer for loop, we're running this k times. And what's k? K is n squared. So this bigger for loop will be n squared n log n. Okay? So, and okay, so then now we have this one, this block. So foo n over 2. So we're calling foo itself, so it's a recursive step. So we do t n over 2, and we run this how many times? N times. So this block will be n t of n over 2. Okay. And bar k, so bar is log of n, right? And we take this n, and we're calling bar of k, which k is n squared. So this would be log of n squared, which would be 2 log n. And we combine all of these into one, which should be 4 plus n 2 log n over 2. And okay. Any questions on this? Is this clear, straightforward? Yeah. So this count as constant work, this one as constant work. So you could do plus of 1. Do we need that constant from what do you mean do we need that? Do we need to include in the recurrence relation? Yeah, so you would want to include the constant as well, to be very precise. Okay, why is t of n a foo? Okay, so t of n is what we're doing is we're representing this recursive function into a recurrence relation, right? So t of n represents the complexity, the recurrence relations for foo, for function foo. And foo n over 4, we're calling foo itself with parameter n over 4. So that's why it becomes t with a parameter of n over 4. Does that make sense? Do we need to solve this relation? I don't know what that was. Sorry. I don't think it's solvable by master theorems. I don't think we would ask you to solve this using master theorem because it's just not solvable. Okay. Why isn't the if statement of and this if statement is of 1. It's a constant operation. Of n is not interchangeable with of 1. Does this make sense? Do you guys all get why if this if block is just a constant operation? Okay. Any other question? Okay, but don't you make comparison and oh, okay. So I think where the confusion is coming from. So we're not okay. So given n, given the parameter n, this operation is only ran once. It's just a constant operation. If this were to be in a for loop that depend on the constant n, then it would be n times of 1. So then that in that case would be of n. Does that make sense? Okay, cool. If the if statement only executes once per yeah, that's a good answer. And since there are 2 of 1s, we only have to write down 1 in our answer. So if you guys want to be really precise, putting of 2 is better for us to grade, but putting of 1 should be fine. Because you know how we drop the constant when it's of 2 and we drop it to of 1? Oh, sorry, of n. It's the same thing. Okay. Any other questions? Okay. So do we? Yes. Well. Well, when we ask you guys this on the exam, we would want you guys to be precise. So we would want you guys to identify block by block. But if it's just a constant, we wouldn't deduct points if you guys just put it over 1. We would be clear on the instruction if it comes up on the exam. Okay. Any other questions? Oh, I like that you guys are answering so many questions. All right, I'm gonna move on now. So, and you can simplify it to log in. All right, so another example. All right, so I'll give you guys around 2 to 3 minutes to do this by yourself. Try to do it by yourself. It's really important to do it because it might come up on the exam. It's a valid question to do so. So try to identify this block, and this block. And other constants as well. Give you guys like 1 more minute. Okay, so let's dive in. So these are all constant operations, right? So these are constant operations. So here we see foo, right? So this is a recurrence step. So this would be T of n over 4, right? But this step is inside the while loop. But if you look at it carefully, we're dividing it by 4. Oh, sorry, we're dividing it by 2 every single operation. And what is that? That's a log of n operation. So this will be log of n, but we start with n of n minus 4, right? And given n minus 4, we're dividing by 2, 2, 2, 2 at each iteration. So we have 4 times t n minus 4 times t with a parameter n over 4, right? So after this step, x is 4, right? Because we have this while, or x is greater than 4, right? So, so foo, we call it with an I, right? But I does not depend on n. It's a constant value because we start from 0 and go up to x, right? So this foo I call will be just t with t1. And since it's surrounded by a for loop, and we know that x is going to be 4, right? And we have foo n over 3, which this should come down to 2, and minus 2. Sorry. So if you add this all up, should be and as we said, we can drop constants, right? Oh, shoot, I forgot. So here we have one operation, right? So this should be, oops. This should be, oh, so hard to use. Right? So and as we discussed, we can drop the constants, right? So we can drop this constant, and this constant wouldn't matter as well. All right, got some questions. Let me see. Oh, that's a lot of questions. Okay, since the offset, since the offset of 4 is negligible with large input size, are Log of n is fine. Boyang asked why this is t of 1. It's because I does not depend on n. It depends on the x, which is a constant. It is important to know that after this while loop executes, x becomes a constant. Okay, you guys are asking same questions again, so I'm just going to summarize it, okay? So, so I'm going to go over this again. Go over the questions that you guys asked. So the first term, so the first block here, this, you guys all now get that why it's log of n minus 4, right? Because we are dividing it by 2 at each iteration. And we start with, we're dividing x 2 at each iteration where x is n minus 4. So the the while loop will be log of n minus 4. And then within the while loop, what do we have? We have foo n over 4, right? So that's t of n over 4. And then what is this? We have a constant operation, x divided by 2. Okay. And then we have t of 1. And as I said, 1 is, this t of 1 comes from foo of I. And I does not depend on n because after the while loop, x is a constant number. So we do this. So we call foo I x times, which is a constant. So it would be, let's say the x becomes 4. Okay, it could be less than 4. So it'd be 4 times t with a 1. But since 4 is a constant anyways, we can drop it, as we learned from like earlier in the lecture. And then you guys got this. I don't see any questions about that. Okay. Any other questions? I'm glad that you guys are asking a lot of questions because this is a tricky question and it is important to get it correctly. Oh, okay. So, but not in the for loop. That could also be counted as or one operation. So actually, I missed that. But that's a good catch because these are all constant operations. Does that make sense? Any other question, or are we good? So is it included in for TL1 already? Sure, you could think of it as like that. It's a constant that is being operated in foo itself, not like and it is counted as on 4 times TL1. Okay. I'm gonna skip now because I'm getting a lot of repeated questions. So if you guys have more questions, come to my office hours because we have to move on. Okay. All right. Okay. So this is the formula that we got, and then we can expand these. And then we drop the constant terms. Okay. So now we're going to talk about vectors. Now we're going to move on to a different chapter, I guess, of this lab, which is vectors and how the resizing and reserving works. So in the lecture, we didn't go over in depth and we didn't really explain why it is so important to resize and reserve if you guys know the size of the vector beforehand. And I'm sure you guys learned the lesson, I guess, from Project 1 that it is very important to do so. So I'm gonna explain why you need to resize and reserve and why it's so memory inefficient and time inefficient if you guys don't do so. All right, so let's look at this example. So let's say we have a vector with items 1, 2, and 3. So the length is 3 and capacity is 4. So what capacity means how much room that the vector can hold, whereas length or the size indicates how many elements there are in a vector. So if you do push back 6 in this vector, on the heap, what it's going to do, since it has one more room, as you can see in undefined, we can just allocate 6 in there. Slide's not open. Okay, there we go. So what happens if we push back 5? Then we don't have more room to allocate 5, right? So what it's going to do under the heap, it's going to create another vector of double the capacity, and it's going to copy all the items in the vector, 1, 2, 3, and 6, and then push back 5. It's going to create a new vector of double the capacity. It's not updating in the Google Meets. Okay, there we go. And then it's going to copy all the elements and delete the old vector and push back the operation that we wanted to do. Okay. So then the size will be 5 now with a capacity 8. So this is what vector does under the hood for C++. So as you can see, when length equals to capacity, then we have to allocate more space in order to push back elements to the vector. So if we know the size beforehand, we could just say, okay, we need this much room, just allocate this much. However, if we don't do that, as we can see, we end up not using this you see the 3 undefined. We end up not using those 3 undefined rooms, and we end up copying all the elements, right? So suppose you want to sort, let's say, 4,100 elements. If you call push back with a resizing or reserving, then the vector will double the capacity will double from 1 to 2, 2 to 4, 4 to 8, 8 to 16, and so on and so forth until 4096, right? And then once you insert the 4097th element, it's going to double to 8192. Then we have what, like 4096 unused element when we could have just reserved 100 elements beforehand. And we ended up copying that much as well. So we ended up copying 1 element, 2 elements, 4 elements, 8 elements, and so on. So do you guys get now why it's so important to reserve and resize the vector? Does that make sense? Okay. Any questions? Okay, how do we know How do you know when? So someone asked, how do you know when to reserve versus resize? It really depends. If you just want, so resize will just allocate with a default constructor. So if you say vector resize without any parameters, just without any value. Sorry, my bad. So if you just call vector dot resize with one argument, let's say like 100, which indicates the element, then it's gonna create a vector of all zeros. And if you prefer that and want to modify from there, sure, you can just use resize. If you actually want to do pushback every single time and just reserve beforehand rather than resize, that works too. What's convenient about resize for vector in C++ is that you can actually give another argument after the size that you want. So let's say you want to resize a vector, so you call vec.resize 100, comma 3, then it will create a vector of size 100 that's filled with 3. So it really depends on what you want to do with it. It just, you have an advantage of being time efficient and memory efficient. Does that make sense? Okay. Cool. So someone asked, so if you resize and then push back, you're going to push after all entries, just allocated, right? If you want to push back elements, you will want to reserve the capacity. Because if you resize, then there's going to be that many elements already allocated in the vector. So if you push back, then it will copy all the element. Yes, yeah, reserve. So you should reserve if you want to push back. That is correct. Any other questions? So that's no. Okay, gonna move on. So we saw that when the capacity is equal to size, we have to copy everything and reallocate everything. So, and that end up costing of one time and space, right? So then is vector pushback the complexity of vector pushback of one then? Of n then? Well, I think that's really pessimistic, right? Because that happens not every single time. It only happens when the size and capacity are equal. So that's when we use amortization to analyze the complexity. So we use amortization when the worst case complexity of the operation is too pessimistic and it doesn't happen too often. So I'm gonna go with over an example with you to illustrate this. So I'm confusing myself. Okay. Okay, so we start from all zeros, right? So sorry, scratch that. So we start from 0, which is which is 0, right? And then when we increment 1, when we do plus 1, how many bits do we have to flip? We just have to flip this one, right? So it'd be 0, 0, 0, 1. So we flip. I'm gonna label cost. So flip just 1. So when we do plus 1, so 1 plus 1, how many bits do we need to flip? We need to flip 2 bits, yes? 0, 0, 1, 0. If we do plus 1 on 2, how many bits do we need to flip to get 3? We need to flip just 1 bit. Because 3 is right? And what about 4? 3 plus 1 is 4, and 4 is 0, 1, 0, 0, right? So how many bits do we need to flip? We have to flip 3 times. So every single time we do +1, the worst case to reach to 4 was 3, right? But does that happen every single time? That's the worst case for sure, but does it happen every single time? No. It normally happens around 1 to 2 times, right? And 3 was just the worst case, which didn't really happen just once here. Okay. So the worst case cost per increment is O of log of n, where it's base 2, by the way. Where n, for example, would be So worst case would be log of n. Since at the worst case, we flip log of n plus 1 bit. So in this example, we did 4, right? So it would be log of 2, 4, which is of 2. And the worst case was actually plus 1, right? Which was 3 bits. However, this does not happen often. This just happened only once. So how often? So we flip the last bit every single time, but we don't flip the second bit every single time. We only flip it every other time. And we flip the third bit only every fourth time, and so on. So we can't say that. It would be very pessimistic to say the complexity for this bit counter would be O of log of n, right? Yes? Okay. So the total cost spent on flipping the last bit will be n times, and we will be flipping the second to the last one n over 2 times, and the third to the last one n over 4 times. So this ends up being so the total cost ends up being 2 of n. And how many operations did we do? We did n times. Total cost, the total operation. Okay, so we divide the total cost with the total operation by the total operation. So we can say that in the amortized complexity for this bit counter is O of 2, which seems to be more reasonable, right? Yes? Does that make sense to everyone? Is someone still confused? I know I mumbled a little bit, but I think I explained it with the bit counter. Okay, cool. Because if you guys are confused, you guys have to tell me or come to office hours later on, because concept of amortized complexity is really, really important, especially when you have to understand the vector pushback, as you're going to go over in the later slide, and any other operations that that's similar to this, where the worst cases doesn't happen often, but we can't. It would be really pessimistic to say that the complexity will be the worst case complexity. So you guys are all good? Yes. So someone asked, is the worst case complexity different from the amortized complexity? Yes, if, for example, in this case where the worst case is not doesn't happen very often, the worst case will be different from amortized complexity. We use amortized complexity when it's pessimistic to say that the worst case complexity is the actual complexity for the algorithm. Okay. Cool. So the reason why I went over this binary counter, which is not on the left slide that we gave you, is because the calendar example is quite confusing. So if that does not make sense to you, try to go over this binary counter example again to really understand the amortization curve. Okay? All right. So we went over this, just a summary of what I said. So relating big counter to pushback. So as we saw, the pushback operation, can we really say that the complexity is of n, which is in the worst case, it is true? But no, but it does not happen often. It only happens when the size is equal to the capacity and we try to push back, right? So let's just illustrate with an example. So let's say, okay, so what this diagram, this figure represents is here we have an empty vector with capacity 1 and we call pushback. Okay? It's dot pushback. And then when the capacity is 1 and size is 1 because we called pushback, let's just say 1, this will be size equals to 1, capacity equals to 1, right? And then we're going to call pushback 1. Okay? And in this case, since size equals to capacity, it would have to create a vector of capacity equals to 2. Since we want to double the capacity, then we have to copy this element, right? And then add this element that we wanted to add. Okay. And then if we call pushback one more time, we would have to copy these element again here, right? Because we would have to create a vector of capacity 4 and then copy these two elements to here and then push back this element. Okay. And then if we do push back one more time, since we have the capacity, we don't have to copy or anything. We just have to add this one. This is diagram or figure makes sense to you? Okay, cool. Thanks for responding to my questions. Okay, so the red ones are the ones that we actually pushed back inserted elements, and the blue ones are the ones that we actually copied because we called pushback when size was equal to capacity. Okay. So these reds and blues are the ones that actually costed it. That actually cost us in pushback operation. So when we call pushback here, right, it cost us copying these two elements and inserting this element, right? So it costs us 2 plus 1, 3 operations. When we did pushback here, it cost us to copy these 4 elements and the element in. Okay, does that make sense? So the red and blues are the actual cost of operations. Okay. Cool. So as we did with the big counter, we summed up all the operations that we did, and then we divided by the total number of operations we did, right? So after we took all the whites and grays, we now have this total number of total operations, the cost, and we're gonna amortize the cost, which is dividing by the number of operations we did. So if you look, now that we have amortized, if you look at each step, it's actually just 1 plus 2, which is just 3 steps, right? So now that we have amortized, now we can visualize that at each operation, it's actually just of one cost, which is much less than when we look at the worst case complexities, right? All right, so amortized complexity, to sum up, amortized complexity explains the cost when some of the operations are expensive, but the majority of operations are cheap. Okay. All right. All right. So one thing that I want to mention is vectors, as we saw, are auto resizing containers, meaning they are gonna, as we saw, when size equals capacity, it's gonna create a new vector and then deallocate the old vector, right? So if you have a pointer to their data, then when they delete the old vector, then that pointer is going to get invalidated. So just make sure to not change the size or capacity throughout the lifetime of the size of a vector or strings or any other auto resizing container changes, because it might get invalidated. Okay. Any questions so far? Okay, no questions. Cool. Okay. All right. Okay, C strings and C++ strings. This should be a very brief overview from 280. So C strings are arrays of characters that are terminated by null character, right? And these are ways to declare a C string. You guys won't be really using C string in 281 projects that much. Mostly, we recommend you guys to use C++ strings, which are which provide very many member functions such as iterators or capacities or accessing operator bracket or even .add, back, front, or modifiers such as like appending, pushback, and they just have so many interfaces for you. So we actually do recommend using C++ string for our project. Okay. Yeah, just take a look at these slides of lab, just a very overview from 280. All right, so handwritten problem for this lab we have is anagram. So make sure to submit your code through Gradescope. And okay, this is it for today's lab. So if you guys wanna ask any questions about the one that like examples I went over, or any questions on projects or labs, feel free to ask them. And if you guys don't have any questions on the handwritten problem, I'm gonna stop recording. Alright, I think we don't have any questions on handwritten.